This is the rack and pinion mechanism. Throughout the second half of the 20th century, it quickly became the foundation of almost every passenger car steering system, primarily because of one key characteristic: its ability to precisely control linear motion through rotation. As the pinion rotates, its interlocking teeth mesh with the teeth of the rack, driving the rack in a straight line. The mechanical advantage provided by this interlocking geometry creates linear motion with minimal sliding friction. But long before its use in steering, the rack and pinion appeared in Hellenistic and Roman engineering as one of the first documented instances of a linear translation mechanism, and it was used in applications from heavy hauling to timekeeping regulation. The rack and pinion would become a staple of mechanical translation for centuries, even finding its way into portable firearms by the 1600s. But as the world approached the Industrial Revolution, the demand for precision would quickly outpace the capabilities of traditional gearing, leading to entirely new forms of linear motion with far greater resolution and mechanical force capabilities, ultimately laying the groundwork for the manufacturing capacity of today. This is the story of precision linear motion. By the late 18th century, the expansion of the British Empire relied heavily on naval dominance and global trade, which in turn relied on highly accurate navigational instruments. However, early Industrial Revolution factories of the era were struggling with a severe production bottleneck: the lack of interchangeable parts. Prior to the late 1700s, screws and threaded fasteners were individually crafted by blacksmiths and artisans using hand files and chisels. A nut made for one specific screw would simply not fit another. Further compounding the problem was the fact that early manufacturing machines were built using these imprecise custom components, imposing their own systematic mechanical inaccuracies to the workpiece. In maritime navigation, this proved especially problematic as instruments that divided a circle into exact fractions of a degree were critical. Microscopic errors could result in the ship miscalculating its position, resulting in catastrophic shipwrecks. The human hand simply could not produce the absolute precision required. The first steps into true manufacturing precision would emerge from a lineage of English engineers, all contributing to the mechanical concept of the lead screw. A lead screw is a cylindrical shaft with a continuous helical thread. When the screw is rotated, a corresponding mating nut travels along the length of the screw, transmitting rotary motion into highly precise, high-force linear motion. The distance the nut travels per single rotation is precisely defined by the pitch of the thread, establishing a mathematical link between rotation and linear translation. The first true breakthrough in mechanizing this concept would come from Jesse Ramsden in 1775 with his development of a device known as a dividing engine, a specialized machine that created highly accurate divisions of a circle in order to generate precise inscriptions of fractions of degrees of arc. To build this machine, Ramsden required screws of unprecedented accuracy of the time. Producing these when no precision screws yet existed to guide a cutting tool was the first challenge. While Ramsden never published how he made his first precision screw, it's likely that it was created from a rough starter screw produced by a clockmaker's screw plate that was iteratively lapped to average out the per-thread errors into a precision master guide screw. With these precise guide screws now created, Ramsden built one of the first true modern screw-cutting lathes. His device combined a lead screw, a slide rest, and a change gear mechanism that allowed the rotational speed of the lathe's spindle to be perfectly synchronized with the linear advancement of the cutting tool. By swapping the change gears, the operator could precisely dictate the pitch of the helical thread being carved into the metal workpiece. Ramsden subsequently used his lathe to cut the screws for his dividing engine. In 1777, the Board of Longitude awarded Ramsden 615 pounds, allotting 300 pounds as a direct reward for his dividing engine, with the remaining 315 pounds requiring him to effectively open source his design by publishing a technical manual and training competitors, effectively breaking his own monopoly to mass-produce precision instruments for the British Navy. Around the year 1800, Henry Maudslay would further refine and popularize the synchronized screw-cutting lathe concept with his own reciprocating screw-cutting lathe. While Ramsden's lathe was a specialized tool made for his dividing machine, Maudslay's lathes were capable of mass-producing uniform, perfectly identical screws, allowing for the standardization of screw thread sizes for the first time. The interchangeability of parts could now be practically applied to nuts and bolts. With reproducibility now established, the next challenge to mass produce precision was measurement. Early metrology equipment was generally large, cumbersome, and incredibly difficult to operate. James Watt had previously attempted to solve this limit around 1772 by designing a tabletop micrometer for validating components for his steam engines. Watt's device introduced the U-shaped brass frame and dual dial system to convert the rotational movement of a threaded spindle into precise linear displacement. A sliding block advanced along a drive screw with 18 threads per inch toward a fixed measuring anvil. As the screw turned, the primary graduated disc tracked the fine fractions of a single rotation, while a second disc, driven by a reduced worm gear, recorded total number of complete revolutions. By reading both dials together, the operator could calculate measurements down to microscopic fractions of an inch. While Watt's design would eventually become the structural progenitor of the modern micrometer, it saw little commercialization. By 1805, Maudslay would develop his own measurement device to validate his manufactured components. Constructed of solid brass and measuring approximately 40 centimeters in length, his device used a pair of precision ground measuring blocks that advanced to clamp the workpiece. The blocks were drawn using a hand-honed precision master screw with 100 threads per inch. This master screw was coupled to a micrometer dial engraved with 100 equal divisions along its edge, resulting in a 1/10,000th of an inch advance per graduation. Within Maudslay's shop, his micrometer served as the ultimate calibration standard and was referred to as the Lord Chancellor. Today, the Lord Chancellor is widely regarded as a foundational instrument in the development of modern precision metrology. By the 1800s, the lead screw became the dominant mechanism for converting rotary motion into precise linear translation across the industrialized world, with its function as a rotary to linear motion linkage being established by a series of geometric and tribological parameters. The lead defines the axial travel per revolution. Pitch specifies the distance between thread crests. The major and root diameters determine the shaft's strength and buckling resistance, and together with the lead creates the lead angle. The number of starts specifies the number of independent helices, the thread form, and the coefficient of friction between material pairings. Together, these elements dictate mechanical efficiency, load capacity, and whether the assembly is inherently self-locking. Self-locking is a critical threshold reached roughly when the lead angle falls below the friction angle, and efficiency drops under 50%. Fine lead screws with a small lead angle, for example, are commonly found in single-start Acme thread configurations and are the standard for precision positioning in machine tools and precision tools, as they provide high mechanical advantage, excellent resolution, and self-locking capabilities that prevent backdriving without external brakes. The trade-off, however, is lower efficiencies of 25 to 40% that reduce operational speed and duty cycle due to heat generation. In contrast, coarse lead multi-start screws with large lead angles dominate applications where speed matters more than holding force, such as in lighter linear actuators and high-speed light-duty positioning in machine tools. While these configurations produce rapid traverse and higher mechanical efficiencies of 50 to 80%, the steep pitch requires more input torque per unit of axial force, and these screws are inherently backdrivable, requiring an external holding brake or constant motor torque. Beyond lead angle, thread form selection also heavily determines the screw's mechanical dynamics and manufacturability. For example, Acme and trapezoidal threads provide broad-based strength for heavy-duty bidirectional loads in machine tools, while square threads maximize power transmission efficiency for heavy screw jacks, but are costly to machine. Buttress threads work well under extreme unidirectional loads, such as in presses, though they fail to reverse load efficiently. On longer screws, diameter must also be considered as it determines both the torsional stiffness of the shaft and its critical whirling speed, the rotational speed at which an unsupported shaft begins to deflect laterally and vibrate. This caps how fast a screw can be driven before the shaft itself, rather than the thread interface, becomes the limiting factor. The mating nut's material properties and geometry also heavily influence the system's overall accuracy and longevity. In nut selection, axial clearance or backlash creates positioning errors, whenever the direction of travel changes due to the dimensional gap between the screw and the nut threads. To mitigate this, anti-backlash nuts such as split nut configurations or spring-loaded dual nuts are used to apply continuous axial preload, forcing constant thread contact. Reducing backlash with preload, however, increases system rigidity at the cost of efficiency and must be carefully balanced against the heat and wear it introduces. Because lead screws operate fundamentally on sliding friction, nuts are typically fabricated from softer, self-lubricating materials like bearing bronze or engineered polymers to reduce friction. They also generally serve as the sacrificial wear element against the hardened steel screw. One of the largest limitations of lead screws is the sliding contact between the threaded shaft and its mating nut, and the inherent friction and energy losses created, particularly when used at high continuous speeds with high loads. This not only requires sufficient power to overcome the mechanical resistance, but the heat buildup can also cause galling, where metallic surfaces cold weld together under pressure. Bringing precision to high-speed linear motion would require eliminating sliding friction entirely and replacing it with rolling friction. In 1927, inventor Rudolf G. Bohm filed a patent that practically solved the problem with a novel screw mechanism that replaced traditional matching threads with a precisely machined helical groove on the shaft and a corresponding groove inside the nut. Between them rode a series of small hardened steel balls. As the screw turned, the balls rolled smoothly through the helical grooves, carrying the heavy load with the efficiency of a ball bearing. What made Bohm's mechanism clever was the integrated return. This was a channel cut into a plate fixed to the nut that diverted the balls out of the working groove at one end and routed them back to the other, creating an endless, closed, recirculating system. In 1936, the Saginaw Steering Gear Division of General Motors adopted this concept for the automotive industry, developing the first commercial recirculating ball screw. The mechanism was originally built for automotive steering and became the foundation of the recirculating ball steering gear used in millions of GM, Ford, and Chrysler vehicles for decades. During World War II, General Motors would adopt the mechanism to flight control actuation on the Boeing B-29 Superfortress. Its efficiency and weight savings proved to be so reliable in high-altitude conditions that it quickly became a popular mechanism in modern aerospace use. Because the friction within a recirculating ball screw is primarily rolling rather than sliding, their efficiency typically exceeds 90% with a dramatic drop in heat generation when compared to lead screws. However, this also inherently eliminates self-locking and allows backdriving to occur even with just gravity alone on vertical loads. The defining geometric parameters of a recirculating ball screw are the lead, the screw diameter, and the ball diameter. Much like a traditional lead screw, lead and diameter together set the lead angle, which governs the trade-off between speed and force, with a high lead moving the nut quickly at the cost of torque demand and reduced mechanical advantage, while a low lead delivers higher thrust and fine resolution at the cost of slower travel. When the balls are recirculated, they are picked up at one end of the loaded path and returned via an external tube, internal deflector, or end cap. This return operation limits maximum rotational speed because the ball must reverse direction abruptly. This limit is defined by a ball screw's DN value, or the ball circular diameter, in millimeters multiplied by the maximum rotational speed. This defines a practical ceiling on how fast a given screw can spin before ball impact and centrifugal effects degrade life and induce noise. In a recirculating ball screw, mitigating backlash with preload is achieved by either oversizing the balls or using a double nut to push the two flanks apart. While this stiffens the assembly, it introduces persistent contact stresses, raising drag torque and shortening fatigue life. Beyond backlash, stiffness in a ball screw is a complex chain of interconnected compliances that encompasses the shaft's tension and compression, the ball to groove localized stresses, elastic deformation, the nut body, and the support bearings. Because these elements rely on one another, reinforcing just one provides diminishing returns if another remains the weak link. The accuracy of a ball screw system is categorized by its lead error and repeatability. The lead error is the deviation of actual travel from the intended path, while repeatability establishes the ability to return to the same position under the same conditions and is typically maintained through proper preload and overall system rigidity. For precision ball screw systems, High speed capabilities introduces its own accuracy issues. As friction warms the shaft from use, the thermal expansion leads to stretching of the lead by roughly 11 to 13 micrometers per meter for every degree Celsius. On a precision machine, that expansion can easily surpass the intended manufacturing tolerance, requiring the screw to be either actively cooled, pre stretched, or compensated for in control. The load capacity of a ball screw requires its own balancing act between two separate ratings. Dynamic rating is the load at which 90% of identical ball screws will achieve 1 million revolutions before metal fatigue occurs, and static rating, the maximum stationary load that causes a permanent plastic deformation of the ball and raceway equal to 1/10,000th the ball diameter. Raising either one means using larger balls or more balls, which trades away smoothness, limits speed, and raises cost. Ultimately, the application of the screw determines how this balancing act of mechanical properties tip. Machine tools, for example, favor high efficiency, stiffness, lead accuracy, and repeatability, while aircraft flight control actuators and missile fin drives prioritize high force, compactness, and reliability. By the end of World War II, high speed precision actuation was now practically achievable, but true total precision linear motion consists of two entirely distinct mechanical tasks: actuation and guidance to support the load and keep it confined to a straight path. The simplest form of linear guidance is the way. These flat or V-shaped sliding surfaces are machined directly into the machine bed and support a complementing carriage. These were rigid and well supported along their entire length, but the sliding friction was high, limiting them to slow speed use. They're commonly paired with traditional lead screws for actuation in manually operated machines. The first major leap came in 1945 with the introduction of the linear ball bushing, replacing sliding friction with rolling friction. Much like a ball screw, a small recirculating circuit of ball bearings roll along a smooth, hardened, cylindrical steel shaft, dramatically reducing friction and making motion far smoother and more precise. However, the round shaft design introduced a new structural compromise. Because the ball bushing wraps fully around the shaft's circumference to capture the balls, it could only be supported at its ends. This created sag and deflection issues. Despite its effectiveness for almost 3 decades, the deflection flaws of the round shaft remained. Ultimately, a new approach to the problem would emerge in the 1970s. Hiroshi Teramachi, who founded the small engineering firm Toho Seiko, would specifically attack the sliding contact and rigidity limitations that still plagued machine tools. Initially, he targeted the tiny clearance looseness between balls and raceways with the development of the ball spline nut. But ultimately, Teramachi understood that no amount of preload could fix the fundamental flaw of an unsupported shaft, especially for submicron applications. In 1972, he would revise the concept completely by replacing the round shaft with a profile rail. By removing the bottom out of a ball spline nut so that the shaft could be bolted directly to a base, the deflection was eliminated. Called a linear motion or LM guide, the Model LSR was the world's first true commercial profile rail linear guide, first commercialized in 1972. By 1973, the Model NSR BC fully merged the spline shaft and mounted base into a dedicated LM rail, and in 1975, the Model NSR BA integrated the spline nut and housing into a single LM block. As CNC machine tools proliferated through the 1970s, the LM guide quickly became essential to the industry, and in 1977 the company rebranded as THK, expanding internationally into one of the dominant global leaders in linear motion. The profile rail it pioneered is now the default linear guide on essentially every CNC machining center and gantry built today. As linear guides matured, two design philosophies on the geometry of the raceway merged: the circular arc profile and the Gothic arc profile. The circular arc profile uses a single continuous radius slightly larger than the ball, so the ball settles into the groove and touches at 2 points. This creates self-alignment and allows the rolling element to absorb surface irregularities and minor installation errors while maintaining high accuracy, easy installation, and very low rolling resistance. However, since each ball carries load in only two directions, it requires 2 rows of balls per side to handle liftoff forces. The orientation of these contact lines splits the design into 2 configurations: the back-to-back arrangement that points them outward, forming an O that resists overturning loads, and the face-to-face arrangement that points them inward, forming an X that tolerates mounting distortion and loads from any direction. The Gothic arch, in contrast, uses two radii meeting at a point, contacting each ball at 4 points instead of two. This raises rigidity but deepens the curvature, which lowers load capacity and demands tighter mounting precision, though it can handle loads from any direction. However, with four contact points, the inner and outer points try to roll at different speeds, so the ball is forced to skid against the rail to compensate. This is known as differential slip, and this can be as high as 40% in certain Gothic arch profiles. Adding preload with oversized balls further worsens the slip, spiking friction and causing premature wear. As a result, the Gothic arch's practical load rating drops to about 50% of a circular arc groove, and its surface to roughly 87.5% in direct comparison. A variant known as the offset Gothic arch attempts to overcome these limitations by using an offset upper row to carry the weight at low friction, with the lower rows engaging only under heavy or sudden loads. To bypass the Gothic arch's slip limitations altogether, many manufacturers employ a compromise composed of multi-row circular arc guides to mimic the multidirectional stability without the slip and reduced capacity, allowing motion to occur with submicron precision and extended life. Even more advanced LM guides would emerge that eliminate point contact altogether. THK's cross roller guides, for example, replace balls with cylindrical rollers arranged in alternating cross directions, which distributes load forces over lines of contact and employ a cage alignment system to keep the rollers evenly spaced to prevent creeping out of position over time. As linear operations began to move into the realm of semiconductor manufacturing, recirculating ball screws and linear guides began to hit a mechanical ceiling. The traditional concept of a rotary electric motor turning a physical screw and subsequently a carriage suffered from positioning errors due to steel elasticity and from particulate contamination caused by metal-to-metal contact. The solution came from British engineer Dr. Eric Laithwaite, who conceptualized slicing a traditional circular induction motor open and unrolling it flat. Known as a linear induction motor, the unrolled stationary coils become a flat track extending down a guideway, while the unrolled rotating cores became a moving carriage. Pulsing alternating current through the coils creates a traveling magnetic field that drives the carriage forward. In Laithwaite's original induction design, the moving member carried a conductive reaction plate, in which the traveling field induced currents to generate thrust. Later, permanent magnet synchronous linear motors would instead place permanent magnets on the carriage, with the field interacting directly with those magnets. As a direct drive mechanism, the motive force is transferred entirely through air gap via magnetic fields. The absence of mechanical transmission results in zero backlash, low friction, and rates of acceleration that were once impossible. While Laithwaite's idea would be incorporated into the development of the maglev train, precision mechatronics variants of the concept, such as voice coil actuators, ironless motors, and iron core linear electric motors, would become the standard for semiconductor manufacturing, where submicron settling at high acceleration is needed. As semiconductor fabrication approaches nanometer scales, linear motion would be pushed to its limits. To keep up with the continuously increasing density of microprocessor manufacturing, extreme ultraviolet photolithography emerged to print nanometer level geometries onto silicon wafers. Because no practical material is transparent to EUV's 13.5 nanometer wavelength, the pattern is not projected through a mask as in older optical lithography. Instead, the light reflects off a reflective mask and is focused onto the wafer by mirror-based projection optics. To keep up with production throughput, the magnetically levitated wafer stage accelerates at 8G, while the reticle stage moves in the opposite direction, peaking at 32G. At these violent bursts of acceleration, the system must synchronize the mask and wafer perfectly, tracking the wafer's position roughly 20,000 times per second with sensors accurate to about 60 picometers, a scale comparable to that of a single silicon atom. Tracking a position precisely with a standard linear motor became problematic as it responds to each reading by firing its coil to nudge the carriage back onto target. Because the motor is never perfectly settled, this constant stream of corrections leaves the stage perpetually overshooting and recorrecting in tiny increments. This residual vibration is known as servo jitter. In photolithography, even a few nanometers of servo jitter is unacceptable. To achieve atomic level precision while minimizing jitter, The piezoelectric effect is used where applying an electric voltage causes a crystal to physically change shape, converting electrical energy directly into linear motion and bypassing magnetism and mechanics entirely. The crystal also holds its expanded state while voltage is held constant, providing extremely stable positioning with far lower servo jitter than a magnetic drive. Modern machines use complex positioning architectures that nest a fine tuning stage driven purely by piezoelectric actuators inside the high speed linear motor stage. This synthesized linear motion uses the piezo drives to provide continuous travel at the nanometer scale, bypassing sliding friction entirely while the linear motors handle high speed, longer range travel. Each leap in precision linear motion has come from removing a source of error. This trajectory points towards motion systems that are increasingly hybrid. As high NA EUV matures and the industry looks beyond it, the bottleneck shifts from how fast a stage can move to how perfectly still it can hold while the world around it vibrates. Future architectures will likely push further into active vibration cancellation, predictive control that anticipates disturbances before sensor can signal them, and new actuator materials that deform with even greater linearity and less hysteresis than today's piezo crystals. Still, even now, the simple lead screw has evolved into machines that can accelerate at dozens of times the force of gravity and still settle to within a width of an atom.